Welcome to another lecture on design and analysis of algorithms. Today's lecture will also be on dynamic programming. The topic for today is the longest common subsequence. Let me start by defining the problem. So, the longest common subsequence will abbreviate as LCS. The input to this problem consists of two strings. So, there is one string A of length m, and another string B, say of length n. I might say string occasionally, but I do mean sequence. So, it does not really matter. The sequence will be a sequence of characters typically. So, I will use string and sequence interchangeably. The output is also going to be a string. Let me call it C and say it will have some length p which is as yet unknown, and we require that C have the following property. So, C should be a subsequence of A as well as B. That is what a common subsequence is. I will define subsequence more formally in a minute. So, C should be a subsequence and we want C to be the longest possible subsequence. So, this is our problem. So, let me define what a subsequence is. So, we will say that X is a subsequence of Y if X is obtained by dropping elements of Y. And of course, the remaining elements which we did not drop should be kept in the same order. So, for example, AD is a subsequence of say A, B, C, D, E. So, these are the elements that we dropped. And as we said, common subsequences are just sequences of both. So, let us take an example of LCS. So, let us say A is the sequence of characters A, B, C, D, E, and let us say B is the sequence of characters say B, C, D, or let me say, let me write it as B, C, E, A, D and some Q. So, they do not have to be of the same length. So, clearly B, C, D is a subsequence of both and therefore, it is a common subsequence. AD also is a common subsequence. So, AD for example appears over here and over here. BCD for example appears over here and over here. So, now you know what common subsequences are. We would like to define what the longest common subsequence is. So, LCS of A and B for example is BCD. You can look through these sequences and you will figure out the only common sequences of length 3 are very few, and in fact, there is no common sequence of length 4, and so therefore, this is a longest common subsequence. In fact, you can see that BCE is also a common subsequence. So, let me just underline that. So, say BCE appears over here and over here it appears over here. So, the goal now is to find one of these common subsequences. So, goal in this LCS problem find any longest common subsequence of A and B. Okay, we don't care which one, but we want one of those. When we speak of LCS, we will mean either every LCS or one of the LCSs, and what we mean should generally be clear by context, otherwise we will explicitly say so. Let me give you a bit of a motivation about why we care about this LCS problem. The length of the LCS of say A and B can be thought of as representing the similarity between A and B. Clearly, the longer this LCS is, the more similar A and B are. Okay. You might ask, why do we care about string similarity? The answers to that are fairly well known and obvious, probably. So, say we have two DNA sequences and we want to know, are they very similar? If they are very similar, maybe there is a common evolution in those sequences. And so, therefore, some measure of similarity is useful. Okay. Suppose we have a misspelt word. We would like to know the word which is most similar to it from our given dictionary. Again, we need some measure of what similarity is. So, even here, the notion of an longest common subsequence is useful. As it turns out, LCS is not the only measure of similarity. There are others as well. But interestingly enough, the algorithms we develop for LCS will be somewhat similar, and you can probably extend them for other measures of similarity as well. Let me start by considering a brute force algorithm for LCS. This is probably a good idea before embarking on trying to discover a complicated algorithm. It at least tells you something. Okay, so if not, you have something to fall back upon. Okay. So, what would be the brute force algorithm? So, the idea would be to say, let us generate all possible subsequences of A. This would be the first step. Then we will check which are also subsequences of B. And then we will retain the longest. As we said, there could be several longest, but we don't care, we will just keep one of those, and that would be the answer that we would print. Is this algorithm good enough? Well, is this algorithm good? Well, it certainly will return an answer, but the question is, will it be fast? Now, it is not going to be very fast because the number of all possible sequences of A is quite large. In fact, you know that if a sequence has length m, then there are 2 to the m possible subsequences. So, therefore, the time for this algorithm is going to be at least 2 to the m. In fact, if you want to write down the sequences, the subsequences, you will also multiply this by m itself. But in any case, this is at least exponential in m. So, that is not what we want. We would like something faster. And in fact, we have said earlier that we are going to apply dynamic programming for this, and our hope is that dynamic programming will give us something better. So, let me review what the dynamic programming ideas are. Okay. So, the first idea was that we should try to express the problem as a search problem. By that I mean that you should clearly identify what the search space is. Okay. So, what is it? What is a possible candidate that you are looking for. Okay, so in our case, the search space consists of common subsequences. Of A and B. Okay, so we are going to search through the common subsequences, and so in that sense, this first step is over. Well, not quite. So there is also one more thing, which is we want to determine the objective function. So what is the objective function? Well, it says of all the elements in the subspace, which is the one that you are going to pick. So in our case, that's easily stated. It is the longest one. Okay, so we have a space consisting of all subsequences of A and B, and we want from it that string which is the longest. Of course, we are not going to generate this space explicitly. We are not going to ever write down anywhere all the common subsequences. That will take too much time. This is just for the purposes of thinking. So let me write that down. So this is only a help in thinking. We are not actually going to generate the subspace, any of these spaces. Then what we are going to do is, we are going to write a recursive procedure. Listed explicitly what the search space is, having defined explicitly what the search space is, the next step is to write a recursive procedure which looks something like this. So it is going to be a search, and it will take as argument the space S which we want to search. And now the procedure typically will divide S into subspaces. Say, let me call those S1, S2, say some Sk. So there are k subspaces. And the idea is that we will find the best in each Si. So by best we mean the element which maximizes our objective function, or which optimizes our objective function. So in our case, it's going to be the longest subsequence belonging to each of these Si's. And then we will return the best of the best. Well, by this best I mean the best computed above here. Okay. Okay. Simple enough. Now the important point is going to be, how do we find the best in each Si? This is where recursion is going to come in. So this, if we can express recursively, will at least have a recursive procedure. Of course, this is not where dynamic programming stops. Okay. So the next step is that we are going to characterize the calls, the recursive calls. So we are going to ask, what are the arguments to the recursive calls? In fact, to all the recursive calls which are made during the lifetime of that recursive procedure. So we are going to define a table then. So let me call it T, which will store the results evaluated for each recursive call. Now, here comes an important switch. Now we are going to ask that we should write a non-recursive procedure and this I am going to call fill, which fills entries of T, okay, assuming other entries are already filled. Okay. In particular, it fills, say, entry ij of t, assuming all other entries are filled. The key time is going to be that the key point is going to be that as a result of this, the total time will be small. In fact, right now I can list what the total time is going to be. So, total time is going to be size of the table times filling time. So, if we can do this with a small enough table, and if we can show that each entry requires only a small amount of time to be filled, then we will have a fast algorithm. And our hope is that this strategy will give us a fast algorithm for the longest common subsequence problem. Okay, so let us see how to do this in the case of LCS. The first step is to define the search space, which we already did. The next step is to write this procedure, and this requires us to divide S into subspaces S1 to Sk. Okay, so let us do that now. Mind you, S is the space of the common sequences of A and B. Okay. So, this is what we are going to search, and now we have to partition it. So, let me write down one strategy. There can be several strategies, and I am just going to write down one. So, one idea might be that I will partition S as S sub A union S sub B union S sub C all the way till S sub Z. The idea is that S sub A is subspace of S consisting of common subsequences starting with letter A. S sub B will be elements of S which start with the letter B. S sub C will be the elements of S which start with the letter C, and so on. So, here is one partitioning. Now, dynamic programming will require us, the idea of dynamic programming will require us to write a recursive procedure which recursively searches SA, SB, SC, and so on, and then pick the best of those answers. This is only one strategy. This will give us a better than exponential time solution, but this is not the only possible strategy. So, let me give you another strategy as well. In this strategy, we are going to take S and we are going to partition it only in two subspaces. So, let me tell you what S1 is going to be. So, S1 is going to be all subsequences which start with the first letter of A. So, remember, A is already known to us, A and B are known to us, and so we can ask questions about what A1 is. So, S1 is going to be all subsequences which start with A1, S2 is the rest, that is start with something else, some other character. Okay. Now, this is the strategy we are going to develop further, but you will see that the idea of this development can also be used for the previous strategy. Okay. So, now we need to define a recursive strategy, a recursive procedure for searching S1. So, our question is how to search S1. Okay, so let me remind you what is S1. S1 consists of all subsequences which start with A1. Okay. So, when we are looking for something, it is usually a good idea to write down explicitly what is it that we are looking for. So, let us say R equal to longest element of S. Okay. So, let us say R has P has length P. Of course, P is not known to us, but let me just define notation P. What else do we know about R? Well, we know that R of 1, the first letter of R is the same as the first letter of A. That comes from the definition of S1. We just said that S1 only consists of subsequences which start with A1. Okay. Now, R is a subsequence of A as well as a subsequence of B. So, which means that R1 must appear in B as well. So, without loss of generality, we can assume, let us say that K is the smallest such that B of K is equal to R1, or actually it is equal to A1. Okay. Now, it might turn out that A1 does not at all appear in B. That is possible. In that case, this search, this space S1 will be null. So, that is going to be a bit of a degenerate case. So, for now, for a minute, I am going to assume that this does not happen and that K is well defined. So, there is some K. Okay. So, now once we know what this K is, what can we say about, can we give something more? Can we say something more about R1? Well, here is what we can say. So, we know now that R of 2 to P is a subsequence of A, well, not of A, because A1 is already taken up by R1. So, the rest of A, so 2 to M, and also of B from K plus 1 onwards. So, it is going to be B of K plus 1 to N. So, this just comes from the definition of R. So, R has to be a common subsequence of A as well as B. The first element of R appears at A1 by definition of S1. It appears at K at BK in B, and the rest of it also must be a subsequence, otherwise it will not be a common subsequence, and therefore, R must be a subsequence of this as well as a subsequence of this. Okay, so, now having characterized what R is, our question is, how do we find R? Okay. Usually it turns out that if you characterize something adequately, it helps in finding. And so, in fact, we are almost ready to find, and in fact, we can claim that since R has to be a subsequence of both, perhaps it is the longest such subsequence. So, let me write that down as a formal claim. So, R, my claim is R2 through P is an LCS of A 2 through M and B K plus 1 through N, where K is, as we defined a minute ago, K is the index of the first occurrence of A1 inside B. Turns out that this claim is true, and the proof is not terribly hard either. The proof is by contradiction. So, let us assume that R2P is not an LCS of this. So, let us say there is some S is some LCS of A 2 to M and B K plus 1 to N. Okay. And in fact, for the sake of contradiction, we have to assume that S is longer than R2 to P. So, that is length of S is greater than the length of this. The length of this is P minus 1. So, let us say it is greater than or equal to P. Okay. Now, the interesting thing is that suppose I consider the sequence A1 concatenated with S. Can we say anything interesting about this? Well, S is a subsequence of A to M. So, this must be a subsequence of A1 concatenated with A2 to the to M, but this is simply A1 to M. Similarly, this is also a subsequence of A1 concatenated with B k plus 1 to N. But what is this? Well, this is nothing but A1 is also Bk, okay, and therefore, this is Bk followed by Bk plus 1 to N, and therefore, this whole thing is in fact Bk Bk to N. Okay. So, what have we found then? Okay. So, we have discovered that this S is a common subsequence of A1 to M and B k to N. But this is itself a subsequence of B1 to N. So, I could just as well write this as 1 to N. Okay. And also S starts with, okay, let me put it here, S starts with A1. Now, what is the length of S? S has length at least P. So, okay, so this really ought to be A1 concatenated with S is a common subsequence of this, and in fact, A1 concatenated with S starts with A1. So, A1 concatenated with S has length at least P plus 1. But now we have a contradiction, because we said that R of length P was an LCS. So, then that means there cannot be a longer sequence which is common to both, but which we have just proved has to be there, and therefore, our original claim must have been true. So, what was our original claim? That R2P is an LCS of A2M and Bk plus 1 to N. So, what is the conclusion from this? So, let me write that down. So, the conclusion is that we know now how to search S1. Okay. So, longest element in S in S1, sorry, can be found as follows. Okay. So, 1, determine smallest k such that B of k equal to A of 1. Second, find capital L equals LCS of A of 2 to M, B of k plus 1 to N. Okay. Why did we do this? Well, this came immediately from our claim. Okay. So, R2P we claimed is an LCS of this. So, we do not know what this is. So, we just find it. So, we just use recursion for it. And finally, return R equal to A of 1 concatenated with this L. So, we claimed that this, we showed that this has to be a longest common sequence of both A and B, such that it lies in S1, and so that is what we have constructed. So, we have constructed a procedure for searching S1. So, the next thing is to find a procedure for searching S2. Well, as before, let us write down what we are searching for. So, let us say we are searching for some r again. So, say again of length p, okay, which is longest in S2. Okay. Can we characterize r further? Well, we know that r is a subsequence of A2 to m. Why 2 to m? Because we know that A1 does not appear in it. So, there is no question of r being a subsequence of the whole thing. So, it has to be 2 to m. Okay. And r is also a subsequence of B1 to n. Okay. So, note that over here we have used the defining property of S2. Okay. So, this is how we have characterized r. Okay. So, at this point it might be tempting to claim or at least conjecture that perhaps r should be the longest common subsequence of both of these. That is a nice conjecture, but unfortunately it is not true. I am not going to explain it in too much detail, but let me just give you a hint of why it is not true, and then you can prove it for yourself. So, just consider A as the sequence of letters A and B say as also the same. Then work out what S1 and S2 are going to be, and then you will see why this is not true. Okay, so R is not the longest common subsequence of both of these. However, something equally useful is true. Okay, so let me write that down. Okay, so what is true is the following. So I claim that R as defined here, okay, is no longer than LCS of A through M and B 1 through N. Okay. I will tell you why this is useful in a minute, but let me prove it first. The proof is actually a single line. Okay. We know that R is a common sequence of both of these. So it cannot be longer than LCS of these two sequences. Okay, so done. Okay. So let me now come back to this conclusion that we have written earlier. So we said that we want to, here is a procedure for looking for the longest element in S1. Okay. So we also want a procedure for looking for the longest element in S2. So let me write that down over here. Okay, so what will that procedure look like? Okay. So I claim that I am going to define R prime equal to LCS of A of 2 through M, B of 1 through N. Okay, so this will be generated by a recursive call, and this is no smaller or no shorter than longest of S2. Okay, so what do we have? We have a procedure to determine the longest element in S1 and an element which is no shorter than the longest of S2. So is this useful? Okay, so what was our goal? So let us go back to our goal. Our goal was to determine the longest of the longest of S1 and the longest of S2. Okay. And of course, so long as, and we would be happy so long as this longer is itself in S. Okay. So this we know, this is what we just said, R, and this is R. What if I put R prime over here? Okay. So this is no shorter, and so if I take the larger of this, it will certainly be no shorter than all of this. And it will also lie in our original space, and therefore this is also, okay, so the longest of S, and so if I substitute R prime over here, that is fine, and therefore this is nothing but longer of the longest of S1 and no shorter than longest of S2, provided this also lies in S. So, if I do this, I will still be happy, okay? And therefore, this conclusion that we have written is good in the sense that if I compute r prime in this way, I just have to return the longer of r prime and r, and that will give me the best answer for the original space itself. So, now we are ready to write down our general search procedure. Okay. So, let me write that down. So, recursive procedure, which I am going to call LCS, it will take as arguments a of 1 through m and b of 1 through n. And now, since we are going to write it as a procedure, let us be careful about boundary conditions. Okay. So, if a equal to null or b equal to null, okay, that is as good as saying, say these are strings of 0 length. So, say the first index is bigger than the second index, return null. So, clearly the longest common sequence of 2 null sequence or 1 null and something else is a null sequence. Okay. Now we have to worry about the main case. Okay. So, let us start by doing that. So, we are first going to see how S1 is going to be searched. So, k is equal to smallest such that b of k is equal to a of 1. Okay. Remember, we are searching S1 and that is what we did. Okay. If k equal to null, as here or k is undefined, that is my short form for that is k equal to null is a short form for saying that, then again will return null. Otherwise, this will kick in. Okay. So, we are going to do all this. Okay. So, we are going to write, or I will just write it jointly. So, we are going to compute r equals all of this. So, let me write that down. Otherwise, we will compute r equals a of 1 concatenated with LCS of a of 2 through m and b of k plus 1 through n. Then they will compute r prime. Now, this time we are searching S2. So, that as LCS of a of 2 through m and b of 1 through n. And then we will return the longer of r and r prime. Okay, so, we will get r and r prime explicitly, we will compute their lengths and will return the longer of the two. Now, I should point out some technicalities. Okay. So, in this call, we wrote down a of 2 through m. The moment we write down a of 2 through m, we are implicitly assuming that m is bigger than or equal to 2, which may not be true. M might be equal to 1. In this case, I am going to assume that an expression like this will be evaluated as null. So, instead of passing, so this expression will be passed as null if m is in fact smaller than 2. Okay. So, what will happen then when this comes over here in the recursive call, a null will be returned, but which is exactly what we want over here, and so therefore, this interpretation is fine. So, I do not have to write that special case whether m is greater than or equal to 2. Okay. It is just handled by saying that this just represents a null string or a null sequence. Okay. So, this is our basic recursive procedure. Now, one possibility might be to write down the recurrence to estimate the time taken for this, and I will let you do that, and you will see that the time taken is actually quite large. Okay, it will be exponential. However, that is not where we stop. Dynamic programming requires us to go further, and that next step is in fact the one which is going to improve the time for us. So, what does dynamic programming require? So, dynamic programming asks us to characterize what recursive calls happen in this. Okay. So, let us look at that. So, first the recursive call is this. After that, there are two recursive calls, right. So, there is a recursive call over here, and then there is a recursive call over here. So, is there any nice property which we know for these recursive calls? Okay. Well, if I look at A, the argument passed for the first string, it is always going to be some part of A, and in fact, the second index is always going to be M. Similarly, if I look at the second argument to the recursive call, it is always going to be a B. Okay. The second argument is always going to be N. The terminal index in that array is always going to be N. And the first index could be anything, it could be k plus 1. And if you recurse again, this property is going to stay the same. So, when we recurse, the key idea is that when we recurse, our calls are going to be something like this. So, all calls which are going to be made are going to have the form LCS of A of I to M, B of j to n. Okay, where I and j could be anything. So, this is an important observation, and this is an important part of the whole dynamic programming strategy. Okay. So, once we know that all calls are of this kind, so let me actually note that down, are going to be of this kind. So, let me write that down. So, say where 1 is less than or equal to I is less than or equal to M, and 1 is less than or equal to j is less than or equal to n. Okay. Dynamic programming says, let us define a table, let us call it T, such that its entries will save the solution answers to these calls. So, Tij will store LCS of A I to M, B j to n. So, actually I am going to use not I ranging over just 1 through m, but over 1 through m plus 1, and j will range over 1 through n plus 1. And the reason for that will become clear in a minute. It will serve as a certain kind of sentinel. So, this will be a two-dimensional table with m plus 1 rows and n plus 1 columns. And now our goal is simply to fill in the entries of this table. Okay. So, once we fill in the entries of the table, T of 1 1 will be LCS of A1 through M and B1 through N, and that is the solution we are looking for. So, if we can generate a procedure for filling these entries, and it has to be a non-recursive procedure, then we will be done, so long as we say in which order the entries are going to be filled. Okay. So, I claim that from this procedure of ours, there is a fairly nice way of filling in the entries. Okay. So, why is that? So, let me define fill Ij as follows. So, what is fill Ij going to do? It is going to fill the entry Tij. Okay. But what is Tij? Tij is going to be the LCS. Okay, let me write that down. So, it is going to be LCS of A I through M, B j through n. Okay. So, let me comment it. Okay. So, this is what the entry is supposed to be. So, fill is supposed to return this entry. Now, if we look at our original procedure, then this is after all a string and this is another string, and we could just as well pass this string or these two subsequences. So, all I have to do is to mimic what happens in this procedure and see how fill should really behave. Okay. So, the first step is, if A is equal to null or B is equal to null, then return null. Okay. So, in this case, what does being null mean? So, being null is simply equivalent to saying when does this expression not have any meaning at all. So, I will interpret that as saying if I is greater than m or j is greater than n, then it does not make sense, and then so we will return null. So, that takes care of that. And the next step is I have to find out what the smallest k is such that bk equal to a1. Now, here the string was starting from the first index a. Here we are starting from I. So, naturally, instead of 1 over here, I should be looking at the ith element over here, because this is nothing but the starting element of the string, and therefore, this should be the element that I look at. So, our corresponding step over here is going to be k equals smallest such that b of k equals a of I. Okay. And of course, k is greater than or equal to j. Why this? Because we want a search to happen from starting from j over here within the string. We do not want the search to go before b. Okay. The next step over here was if k equal to null, then return null. Okay. So, we could put that in, okay, but we do not, as it turns out, we do not need to. Okay. So, the next step is going to be r is equal to a of 1 concatenated with this LCS. But remember that we do not want any recursive calls. So, we cannot write fill of all of this. However, we are allowed to assume that the table is already full. So, in which case what can we do? We can write over here T of a of 2 through m, but a of 2 through m has to be interpreted in light of this a of 1 through m, which in our case is I through m. So, this 2 through m really is nothing but I plus 1 through m. Okay. So, in fact, we will be writing, instead of writing a of 2 through m, we will be writing T of I plus 1 comma k plus 1. Okay. The next thing is r prime, and again over here instead of LCS of 2 through m, since we started off with a which is going from I through m, this will be I plus 1, and this is not going to be 1 through n, but this will be j through n. Okay. So, this will mean that r prime will be slightly different. So, r prime will have to be table entry, not LCS again, but the table entry. So, I plus 1 comma j. Okay, so, this is what it was. And now, we are going to return the longer of r and r prime. So, now we are essentially done. So, we have written the fill procedure. So, let us just see how the fill procedure is working out. Okay. So, let us look at our table. So, this is our table. So, in our table, say I is going in this direction, j is going in this direction. Okay. The first step is if I greater than m or j greater than n, then return null. Okay. So, this step essentially says that if this is the m plus 1th entry So, this part of the table and this part of the table, so this is the n plus 1th entry over here, are going to be all nulls, this entire thing. Okay. Now, if we look at ij, how to fill ij, it depends on I plus 1, k plus 1 and I plus 1 and j. These are the two table entries it depends upon. So, let me write that out. So, if I want to fill, so this is some index I, and if I want to fill this, so this is this j over here, then this entry is going to depend upon I plus 1 j. So, it is going to depend upon this entry. So, let me write that as an arrow over here, and it will also depend upon I plus 1 k plus 1. Okay. So, just going back to this, it depends upon I plus 1 k plus 1 as well. Okay. So, I plus 1 k plus 1 would be something in this. So, it would be some entry over here. So, it would also depend upon this. So, if I want to fill this entry, I need to have these entries already filled. But that is very easy. How do I do it? Well, if I start filling the entries from the bottom, then I am essentially, then I will ensure that when it comes time to fill these entries are already full, and then the fill procedure will work correctly. So, that is all. So, that is what I need to write down next. So, all that is very simply done. So, I just want to tell you what the code is going to look like. So, first I want to make sure that these two things, these two are properly set. So, that will be done by saying for I equal to 1 to m plus 1, what happens? T of I comma n plus 1 is equal to null, and for j equal to 1 to m plus 1, T of m plus 1 comma j is equal to null. That just sets the bottom row and the right hand side column to null. Now comes the main point. So, for I equal to m to 1, for j equals n to 1, we will just fill T I j is equal to fill of I j. And because our rows are going m to 1 backwards, we will make sure that fill of I j will find the table entries already filled properly. So, that takes care of the whole thing. So, at the end of this, we simply return T of 1 1. That is going to be our final answer. Okay. So, what remains now is to estimate the time taken. So, this time is going to be simply O of m, this is going to be O of n, and this is going to be O of mn because of these two loops over here, and the time taken for fill I j. So, how long does fill I j take? Well, the only place where time is taken, there are two places where time is taken. Okay. So, one is this. Okay. So, this could take time proportional to the length of b. So, this could take time proportional to n. Okay. What about this? So, we are going to do the concatenation. Now, if you store the subsequences which have been computed as arrays, then this would take time O of m, okay, because we are going to take the subsequence and we have to concatenate it. Okay. Or in fact, it would take time, it could be that the subsequence is the entire thing. So, it could be max of m and n. And maybe computing the longer will also take time this much. So, overall the time taken for this is going to be O of max of m and n. Okay. So, coming back, this last part fill is going to take time O of max of m n, and so the total time is going to be the product of these two things, or in other words, total time is equal to O of m n times max of m and n. Okay. Now, let me just, to summarize, let me just say that I have given you a dynamic programming algorithm which runs in so much time. Okay. There is a simple modification that you can make to this, using which you can reduce the times further. So it can be reduced to time O of mn. So I am just going to write down the code for fill, and I will not prove its correctness, but the correctness will be proved in the manner analogous. It will be only slightly more complicated, and so I will just do that and I will stop this lecture. So this is the code which will give you a faster result. It will require that you store the result being calculated. The table entry should be stored as a linked list rather than storing the entire subsequence in each entry in the table. Store it as a linked list. If you do that with a little slight trick, you should be able to reduce the time taken just down to O of mn. Okay. So with that, I will stop this lecture. Thank you.